All right, so in this example, we're going to be applying Bernoulli's equation in order to solve for the velocity at the exit of a siphon. This is sort of like what you would do if you wanted to empty a swimming pool or something, where you take a tube of water, make sure that it is entirely full of water, so no air bubbles or something in there. Um, for example, by submerging it inside of the tank, um, and then you can pull it out of the tank and get flow through the tube. And so we're going to look a little bit at how a siphon works using Bernoulli's equation. So to start with, we're going to list our assumptions, right? Um, and we're told that Bernoulli's equation is valid, right? Um, and that really has bundled into it a whole bunch of different assumptions that we should be aware of before we're going to be applying Bernoulli. And so, in the way we derived it in class, first we assumed steady state, right, or d dt equals 0. I should note that there is an unsteady form of Bernoulli, but that just kind of goes beyond the scope of what we've discussed so far. Second, incompressible, right? So we're assuming that, for example, density is constant within the fluid. Um, Three, we're assuming that this is frictionless, no heat, no work. Remember, essentially the way that we derived Bernoulli in class was first by doing an energy balance, and then we went ahead and just dropped out those friction, the work due to friction, any heat input, and any other kind of work on the system. Dropped out all of those terms. What we're left with is what we call the Bernoulli equation. And then four, we need to assume that the flow is 1D or along a streamline. In this case, we can imagine having a streamline that traverses the entire system, starting from Z1, moving to Z4, and to Z3, and then out through Z2. Um, and so we can apply the Bernoulli equation because we can just follow that streamline through the system. Okay, so now to get started in A, we're asked to find an expression for the velocity v2 exiting the siphon tube. And so let's start with writing out our Bernoulli equation for part A. So we're going to write that P1, here, I'll write this out in general terms, PA over rho plus VA squared over 2 plus GZA is going to be equal to PB over rho plus VB squared over 2 plus GZB. Right, and so that's basically just saying that this pressure term plus this kinetic energy term plus the gravitational potential energy term within the fluid is constant. But now the first question that we have to answer in order to start trying to solve this problem is what is A and what is B, right? So what are we going to choose for A? And in general, to get started on something like this, you want to ask yourself, where do you know, where do I know the all of these terms or most of these terms um, in the problem? And where do I want to know these terms? And so, for example, we know that we want to find V2, right? That's what we're asked to find in the problem. And so we're going to let um, B equal 2, right? So we're going to substitute subscript 2 in here on the right-hand side. Now the question is, what should 1 be? Um, and, we have a couple different choices, right? And in part B, we're given, all of these different Z heights. So we certainly are going to have enough information about Z. Right? We have Z1, Z2, Z3, Z4. But if we look at this problem a little more closely, we'll see that we don't really know what the pressure is, for example, at Z3 at the outset. But what we do know is that we have at Z1 we have this water, right, that's exposed to atmospheric pressure, and so we're just going to assume 5 here. We're going to assume that the pressure above the tank is PTM. And if we make that assumption, the pressure above the tank is P atmospheric, which is a pretty reasonable one. And now if we look here at Z1, we would know the pressure, we know Z, and now we just need to figure out what that velocity is. And since this tank is large, and we can assume that the tank is large relative to the tube diameter, then we could assume that V1 is equal to 0, right? Because this tank is really large. And one way to think of this is that if we have a little tiny tube coming out of a really big swimming pool, despite, if we have even if we have a really high velocity of liquid that's flowing out of the tube, we'll have essentially 0 velocity of that upper surface moving. And so if we let A be section 1, and we assume that the tank is large relative to the tube diameter, then we'll end up with this term dropping. So if we do that, we'll just rewrite this. Now we have P1 over rho plus V1 squared over 2 plus GZ1 is equal to P2 over rho plus V2 squared over 2 plus GZ2. We said that this is going to drop out. Another thing that we notice is that at this outlet here, we have a jet exiting into atmospheric pressure, and that means that the pressure here is going to be atmospheric. And so P2 and P1, these two terms cancel out with each other on the left and right hand side. And so the only terms that we're left with are these potential energy terms, GZ1, GZ2, and that thing that we're trying to solve for, that V2. So we can work this around, right? We'll get that, for example, V2 squared over 2 is equal to G times Z1 minus Z2. Therefore, we end up with V2 is equal to square root of 2G times Z1 minus Z2. So there we go. And this is telling us that the velocity at the exit of the siphon is going to be related essentially only to the difference in height. And if we have a larger difference in height, we're going to drive a larger siphon velocity at the end. This kind of makes sense, right? If we imagine doing this in real life, or if you've ever done this yourself, you'll see that if you move the siphon tube down lower, so if you were to lower Z2, then you end up increasing the velocity. And if you raise it, then you decrease the velocity all the way up to the point where if the exit tube is level with the surface of the fluid, then the velocity goes to 0. In fact, if you raise it up above, then you lose your siphon altogether. So this makes sense, right? So now in part B, we're just asked to plug in some numbers, essentially, right? Tube is 1 centimeter in diameter, Z1 is 60 centimeters, Z2 is minus 25, Z3 is 90, Z4 is 35. Estimate the flow rate, right? So we're talking about volumetric flow rate in centimeter cubed per second. So let's kind of quickly go through this, but we should note here that we're given, for example, Z4 and Z3, even though they don't actually play a role in what our final answer is. So it's kind of like a red herring here in this problem. So let's look for part B. We're really just going to plug in our numbers, right? So we're going to now have first we want to find V2, and then once we have V2, so first we're going to find V2, then we're going to have Q2, right, or that outlet flow rate is going to be equal to V2 times A2. So first to find V2, we're going to have V2 square root 2 times 9.81 meters per second squared times, and the difference in elevation, let's see, so Z1 is 60 centimeters, that's 0.6 meters, and minus, we're given that Z2 is minus 25 centimeters, so that's minus 0.25 meters, and if we work all of that out, we're going to get that V2 is 4.8 meters per second. And if we go down, so now that we have V2, the next part of our solution method is to say that Q2 is equal to V2A2 is equal to 4.08 meters per second times, and now we have, just to figure out the area of our tube, and we're given that the tube is 1 centimeter in diameter, so we're going to have d squared times pi over 4, so it's going to be pi 4 times the diameter, 1 centimeter, 0.01 meters squared. We work this out, we get 321 times 10 minus 6 meters cubed per second. We can convert that. So for example, we can say 321 10 to the 6th cube, 321 times 10 to the 6th meters cubed per second, times, we know that we have, so it's 10 to the minus 6, and we know that we have 100 centimeters per meter. And so if we cube this, we end up with meters canceling out, and we end up with 321 centimeters cubed per second. Right, so there we go. Those are our answers. All right, so a nice application of the Bernoulli equation. As the text mentions, we are going to revisit this when we get to chapter 6. And we're going to deal with, for example, what happens based on friction in this tube. Right, so remember in this problem, we assume that the work due to friction is equal to 0. Right, because in order to apply Bernoulli, we have to assume frictionless flow. But our intuition tells us that if we were to take a really, really long tube, then we should get a lower flow rate. So for example, if you were to take a 3-foot section of garden hose, you would imagine that you should get, for a given elevation of the outlet Z2, you should get a higher flow rate than if you have a 100-foot garden hose, right? Because it's just so much longer and narrow. And what your intuition is telling you there is that the work due to friction can actually be pretty significant in this problem. We don't yet have the tools to deal with that, to deal with this, the friction term in the energy balance, but we will get there in chapter 6, and when we do, we'll revisit